Hi, welcome back to our new session. Well, last time we had discussed about the product rule and the quotient rule, right? So we have seen some other derivatives, right? To wrap up, what do we have? The derivative of constant respect to x is 0. A derivative of x to the n, right? That's our power rule, is power taking back x to the n minus 1. Right? That's what we had for power rule. And something else still applied. Right? There's some scalar multiply. Scalar multiply, we could use coefficient a or b. Right? Scalar multiply, getting a linear combination of the derivatives, right? And so on. We get what else? Derivative of sine cosine. Negative sine. Tangent. So get a secant square. And the cotangent derivative has negative cosecant square, and derivative of secant is secant tangent, and for cosecant is negative cosecant cotangent. That's what we have for the trigonometric function. Then also we have the product rule that the product of u times v will be u prime v plus v prime u for the first derivative. And the quotient rule is the quotient. That will be similarly as product rule minus v prime u over the square of v. Right, again, if this one, if you want to prove it, use the product rule, we still also have the limitation, right? And this one we have, if we prove the cotangent or cosecant, right? If we prove the cosecant by the power rule, that will be causing a little trouble, right? So that is something we see. But to wrap up, that's everything we had so far. We showed these formulas, we showed these ones, right? And I ask you to try those things, right? To see if you can do them. Right, that's everything we had so far of the formulas. Then we had talked about the higher order derivatives. Like usually up to second order is commonly used and have a lot of meaning in geometry, which we'll see later. The meaning when we graph them, or when we require using the properties to graph the function, we'll see. And besides, right, for some limitation, which we'll have introduced, we will introduce some other properties. We'll see later, and we'll see more examples, right? Something left over in our third section. We will have to do like find the fourth derivative for y equal e to the x cosine x. Right, so we do not know what we were gonna get, but that is the y of the equation. Right, so find the first derivative, we need to apply the product rule. Right, so for e to the x cosine of x, we let u prime to be e to the x, and u to be e to the x, and v to be cosine of x. Therefore, our u prime is e to the x, our v prime is negative sine of x. Right, therefore our first derivative y prime is u prime v plus v prime u, right? That's e to the x cosine of x plus e to the x, or if we follow the order, right, negative sine of x e to the x. And that we get the y prime to be this. In the case that if we deriving the or differentiate the e to the x cosine x, we have two terms, e to the x cosine x minus e to the x sine x. So it's like if we have a little observation, right? When we see, well, e to the x to take derivative that's same. When we see the cosine x or sine x, then we take derivative that will be like a loop of going to sine or cosine going to sine and cosine, 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 sine, cosine. They just going back and forth, of course with different signs, different coefficient of signs in front of it, positive or negative. Therefore, well, the second derivative we expect to differentiate e to the x cosine x, we have it already. Right, so the derivative of e to the x cosine x is e to the x cosine x minus e to the x sine of x. Right, that's what we get for e to the x cosine x. Then maybe we find a higher order derivative, we're still gonna have the loop of e to the x cosine x or e to the x sine x later with something else, right? Then when we find e to the x sine x over here, we may have second derivative left over something with e to the x sine x and e to the x cosine x. Well, then what we could do is to find the derivative for e to the x sine x. We do the same thing, u is e to the x, v is sine x. U prime is e to the x, v prime is cosine x, right? So d dx of e to the x sine x is e to the x sine x plus e to the x cosine of x. That's kind of, we get is the loop, right? When we do differentiate e to the x cosine x, we get this. When we differentiate e to the x sine x, we got these. And when we find a higher order derivative of e to the x cosine x, we'll have both of them at least involving in our expression, right? That is only those things left over. Right? So that's our first derivative. When we find the second derivative, is simply differentiate e to the x cosine x and differentiate the e to the x sine x. Like we can just use these sort of expression or formula, but not exact formula, but we develop to use them temporarily, right, for this question. Right, therefore, e to the x cosine x, differentiate that, we get the term of e to the x cosine x minus e to the x sine x. And the derivative of e to the x sine x is also written right, e to the x cosine x to differentiate and e to the x sine x to differentiate, get these two. Right, then afterwards we just simplify them. It is not necessary to leave this step if you can just directly see what will happen. But to expand out is always a little help, a little benefit that we have e to the x cosine x are same term to be cancelled, right, opposite sign. And we have the negative e to the x sine x. That's negative 2 times e to the x sine x. Right, to be our second derivative. And as for the third derivative, that's negative 2 times derivative of e to the x sine x. That's e to the x sine x left over for the second derivative, then negative 2 times the derivative of that. Well, we could leave that expression, don't have to multiply out since we have the e to the x sine x plus e to the x cosine x as the expression simply what we have. We don't have to do the extra step to multiply out since we need to find the derivative. Now e to the x sine x derivative, e to the x cosine x when we get e to the x sine x, we have derivative of plus e to the x cosine x, and that's positive sign, so we could express that out with no problem. We don't have to put parentheses. If you want, you could write extra line. What that we get is this expression, just copy down whatever we had for e to the x sine x and for the derivative of e to the x cosine x as we had seen before. Right, and then what we left over is some term cancel, some term being combined together. That is negative 2 multiply twice of e to the x sine cosine x, which the fourth derivative of this expression will be negative 4 times itself. The fourth derivative will be negative 4 times e to the x cosine x. Right, so that is, I think, a good enough example to see the higher order derivatives. Right, if for polynomials it will be a little easier. I just apply simply power root to everything, and when I apply the power root, the power will be descending, and maybe or may not at the end will get to 0. But here, for exponential and for trigonometry function, exponential give us same thing. For every derivative, trigonometric function, especially sine and cosine, will give us the opposite term, right? Not opposite, but the certain thing, right? Cosine and sine are just going back and forth. Look at that. Alright, so that is the property to get. And basically that is how we find the high order derivatives. And let's see the next example. Right, to verify this y equal 3 cosine x plus sine x, satisfy the differential equation y double prime plus y equals 0. Right, so we have some equation like involving derivatives, maybe the ordinary derivative or something called partial derivative, which we'll not touch in this course anyway. But this one is called differential equation involving the derivatives and maybe the y original function or maybe some expression of x inside the equation is called differential equation. I will not touch differential equation anyway, but to verify is a basic work to verify. So what we want to check is y double prime plus y equals 0. So we're given y is 3 cosine x plus sine x. So our purpose is to find the y double prime and add that together with y to see if that is equal to 0. Right? So first of all, find the derivative of y. That's 3 times negative sine x plus the derivative of sine x is cosine of x. I don't have to put parentheses. That is negative 3 sine x plus cosine x. Then y double prime will be the derivative of the first derivative, right? That second derivative. That will be negative 3 times derivative of sine is cosine of x. Derivative of cosine is negative sine of x. That is negative 3 cosine x minus sine of x. Well, even though it's apparently combined together will be 0, but we still need to show that. Right? Do we have the equation holds for 0? So when we prove equation holds, we need to check is the left side and right side separately. So we don't know, separate them. Y double prime is the expression of negative 3 cosine x minus sine of x. Y is the expression that's 3 cosine x plus sine of x. Are these two? Then we get negative 3 cosine x, negative sine x. Then it gets line by line, right? We get this one is 0, this one, when we combine is also 0, 0 plus 0, that is 0. On the right, it is 0. Right? So 0 equals 0, so verified. And that's how we verify the equation when we substitute our terms into that, right? Such things want to verify a solution for differential equation that's how we do them, right? Find the derivatives required in the expression, then to check separately on each side. Right, so that is our chapter 3.3. About product, quotient, rules, and higher order derivatives. Then the fourth section in chapter 3 is the chain rule. So for the equation that is composite equation, y equals f of g of x, we collect y to be f and g of x to be u. Then this y will become f of u, but still the f of g of x. And the rules say, well, to take the derivative of composite function, that is f of u, and the composite inside is g of x su, that we can take is the derivative of y respect to u first, then we take the du over dx, which is a step-by-step differentiate. Or if we in a composite way, the dy over dx of f of g is we take the derivative of f has the variable s to g of x, then we multiply a term of g of x derivative, and multiply a term of derivative of g of x. That is somehow the chain rule is doing, right? So we need to, like whatever, everything we see before was a simple expression, like even though the product rule and quotient rule, that is still the either linear combination or just functions that have the arithmetically combined together. Right? But here, for this new section here, what we discuss is the function of composite function, and the derivative of that, what we do is step-by-step differentiate. Like in maybe inappropriate example that for example, right, not that much appropriate, but I show you that I have a bag, and surely what I put in is another bag, and in another bag I have a charger, right? So what I can show you is, well, I have a small bag, and inside the small bag I have a charger, right? So I put in to the bag, and I put in the big bag, right, to seal it, right, to save it. So the next thing is to reach the charger inside my bag. What I need to do is I need to open the bag first and take out the small bag. Then in order to reach the charger, I need to open this small bag, and then to reach the charger I want. Right? So it's like these things are composite together, and in order to reach the charger, I need to reach them step by step, right? To get one taken out and to get another one being taken out. So that is somehow a not very appropriate example, but can explain this one a little bit. Step by step doing the stuff. Right, but anyhow, I will see some detailed example. But first thing is to analyze the composite function, right? How they are composed. For example, f of x equals 1 over x plus 1 is itself a composite function. Right? So to decompose it, what we get is a rational function, right? So that is 1 over u, and the u is x plus 1. Right? So that is composed the u into our x, our u is x plus 1 into the fraction here. Right? So for y equals e to the sine of 2x, so basically it is a function of exponential first, that is e to the u. Then u is sine of 2x. Right, but sine of 2x is not a simple function, it's still composed by sine of a variable, which the variable is not simply the x, is the variable of v, where the v is our 2x. Right, so it is not a single variable of x, it is an expression of x, then we compose together. Right? It is not e to the x simply, it is e to the sine of 2x. Then the sine of 2x is another function composed into the exponential, and inside the sine, the variable is not simply x, it is 2x. The way we composed is compose v to sine x and compose the sine x into the power of exponential to get this one as the exponential function. Right, for something else like f of x to be tangent square of 2 minus x. Right, first of all, that's the square of tangent x. We have the square of tangent x. Right, we have tangent square of 2 minus x. Basically, that's the square of tangent, which is the power here. Right? Then our u is tangent. If you write it a little more detail, right? That's the square of tangent x. And our tangent is not simply the variable x, it's the variable of 2 minus x. It's composed with 2 minus x inside. And our last variable is the 2 minus x. Right? The composed in and composed in. Right, so that is the somehow the composite function behind it. Right. So once again, right, for everything the variable is not x, that is a composite function. Like we see the exponent, right, what we usually have is e to the x, but here is e to the sine 2x. That is not variable x. So we need to differentiate not only the exponents, not only the e expression, but also the exponent afterwards. Right? And also we have exponent to be sine x, sine of 2x actually. We not have x inside the variable, so we have another composed 2x with the variable of sine. That is not x. So only, like what we had the property or formulas before, only we can see is the variable of them, either tangent x, secant x, or sine x, e to the x, x to the n, these things have variable of x only. But for anything that input is not x, is called composite function. Now we'll see how to take the derivatives. And the rule here, right, just the composite function will be f prime of the derivative of the function, whichever variable is composed, multiplied by g prime of x. Right, so let's see the thing left over last time. Right? Last time we see, well, the cosecant variable, right? The derivative of cosecant is the derivative of cosine to the negative 1. Right, cosine to the negative 1, that's what we get for the cosecant. Right? To find that derivative, we say use power rule, but that's negative 1 times cosine x to the negative 2. And this time we know that, well, this is not only the power rule we apply, right, but inside is cosine of x. So we need to multiply the derivative of cosine that cosecant is sine actually. Maybe I also put it wrong last time. It's sine. I finally find out my mistake. It happens. Well, the cosecant is 1 over sine, and derivative of that, right, apply the power rule, since that is the negative first power we take down, and negative 1 minus 1 is negative 2. But when we see the chain rule here, right, we know that we need to apply the derivative to the inside function as well. And now we will get is negative 1 over sine square of x times cosine of x. Right, and we can separate them to be negative 1 over sine x, cosine x over sine x, negative cosecant, cotangent. Right, that way we'll apply the chain rule here actually. We're able to resolve the formula nicely. Right? Otherwise, what we get will be just negative cosecant square of x. That is not the true formula. Right? We have to multiply the derivative of whatever is composed inside. Right, so compose step by step, and we need to deriving or differentiate the function step by step. That is what we see. So for the example that a little trick here. We had analyzed that, well, this one is e to the something exponent, then u is sine of v, then v is 2x. Right, step by step, that is what we have. Right, so find the derivative of f of x. Use the chain rule. It's also a step-by-step differentiate. First of all, the derivative of e to the something is the same e to the sine of 2x. But we need to multiply the derivative of sine of 2x. Right, that's our first step. E to the u will be same e to the u, right? E to the x derivative is same e to the x. So e to the sine x, we have e to the sine x. But since the variable is a composite, is another function basically, so we need to multiply the derivative of it. And the derivative of sine is cosine. But the variable of cosine is not x. The variable of cosine is also a function, which here is 2x. So what we'll get is e to the sine 2x cosine 2x times 2. My derivative of 2x is just 2, right? Nothing else being composed. Here is not composite function, but just a linear combination. It's a scalar of x. I'll take the derivative. Then we'll get 2 cosine x e to the sine 2x. Just simplify a little bit. That is what's this one doing. Right, so just follow the step by step and observe carefully what do we have, right, is the thing. So find the derivative. For f of x equals x squared plus 1 to the third power. Of course, you can expand that, but not necessary. Right? So to find the derivative of that, what we can do is f prime of x to be apply the chain rule first. I mean the power rule. That's 3 times x squared plus 1 to the second power. Right? Because we have 3 taking derivative, that's 3 times the inside to the second. But recall that, well, inside is a expression, so we need to take the derivative of it. Right, so step by step differentiate. Right, the most outer piece is the cubic function, then the inner piece is another expression of polynomial. Right, this expression just a linear combination of terms. So I have 3 x squared plus 1 to the second power multiplied by what we have is 2x plus 0. Right, the derivative of x squared plus 1. So we multiply, that's 3 times 2x is 6x. X squared plus 1 to the second power. Right, if you can try to expand that second power multiplied by 6x, it will give you the same result as you expanded first the perfect cube and taking the derivative. Right, that will yield to the same result, but here hence a little much easier. Not only a little, but much easier. The only thing is don't forget to differentiate the middle part, right, the inside part. And if we see rational function, here we don't have to apply the quotient rule. Right? The quotient rule is function attached over a function. Here is the coefficient over the function. What we can apply is the power rule. To find the derivative of this function, we could simplify it. Negative 7 times 2x minus 3 to the negative 2nd power. If I just flip the power up, then we get a scalar multiplied by the expression. And this expression is a power. Right? We have inner piece is not x, but outer piece is negative 2. So the derivative of it, that's negative 7 times negative 2 times 2x minus 3 to the negative 3. And that is the derivative of 2x minus 3 to the negative 2, simply just the power rule, but not yet. What we need to do, since the inside is not x, we need to have a habit that every function, we need to check if the variable is x or not. Right? We have the inside is 2x minus 3, then we have to apply the chain. Right, so we get 14 2x minus 3 to the negative 3 multiplied by the derivative of 2x is 2, the derivative of negative 3 is 0. At the end we get 28 over 2x minus 3 cubes. And that's what we have. Right, so actually just the first step when we're taking the derivative, we need to be super careful. Right? Afterwards it's what it's supposed to be. Simplify or apply the rule or formula to it. But the basic thing is if we have composed function, we do step by step, we get that. And of course, it doesn't show us if G is another composite, we do it, apply the rule again, right? Like what we see in the first question. Right. Then we see the next one. Like we're breaking step, we also see the tangent square of 2x. Well, basically that's the square of tangent x, u square, and we have tangent of v, and the v is 2x. Right, step by step, it's composed that way. Right, v and the u. So still, if we not that much clear of that, we can make it a little bit more clear. That is the square of tangent 2x. Right, then we take the derivative to tangent 2x to the first power, right, since that's multiplied by the derivative of tangent 2x. Right, that we get 2 tangent 2x multiplied by the derivative of tangent is secant squared. And multiplied by the derivative of inside is 2x. Two tangent 2x secant square 2x 2, that is 4 tangent 2x secant square 2x. I just do the composite one by one.